It beeped. That's a good sign. So last time we went through the first few sections of Chapter 2. I think we got through 2.5, which got us through the normal distribution and the empirical rule. We talked about z-scores, right, and how to compute a z-score. Okay. Oh, I know where we stopped was quantiles from a normal distribution. So what does that mean to say a quantile from a normal distribution? What are quantiles? Okay? Quantiles is the top word, generic. So it's a quartile is one type of quantile, and a decile is a quantile, and a quintile, and a percentile. Anything with an "ile" on the end is a type of quantile. So basically, a quantile is a value that has a certain percent below it, right? So a quantile is a value from a distribution, like from a normal distribution or whatever, with a given percent of population below it. Now, when I use the word percent, I'm sort of saying percentile, but you know, if you do quartiles, then it's a quarter of the population, or 1/4, or 25%. So anything that you could say in terms of a quantile can be put into percentiles, but that's what we mean by quantiles. So if I have a normal distribution, and last time we were talking about, did we use height? Is that what we were doing? Right? And it was 70 inches. We use 70 inches as the mean. Okay. So 70 inches with a standard deviation of 3. And remember, halfway down the hill is approximately 1 standard deviation. Remember the 68%, 95%, 99.7%. All that, okay? So what height has 84% of the population below it? 73. He's just better at math in his head quickly than you guys. And where'd you get, how'd you know that?
The 70 is 50 percentile, and yeah, half of 68, and let's figure out what you're at.
Yeah, below here is 50%. If 68% is in the middle, then how much is not in the middle? 32%. And so by symmetry, half of that 32% is sitting up here in this tail. So that's 16%. So if there's 16% here, there must be 84% down there. So 73 is the 84th percentile, right? So what is the 85th percentile? I gave you one you can't do using the empirical rule, right? So you need a calculator. What you need is the inverse of the normal distribution function. The normal distribution function gives you the percent that's below a certain value or between certain values. But the inverse, then, you give it a percent and it returns a value that has that percent, right? So I wrote P85, that's the notation for percentile. So capital P sub 85 means 85th percentile. On your calculator, you do that with the inverse norm function. And if you have a TI-84, then the inverse norm function works with 3 arguments. And the first argument is the percentile, the amount you want below it, 0.85, and then the mean and the standard deviation.
Population.
Yeah, the parameter for the distribution that you're talking about. Right? So, has anybody got it done? 73.1. So 73 even is the 84th percentile, but 73.1 gets you to the 85th. So you got another 1% of people that are 1/10 of an inch taller than that. Right? So if you want to use a normal table in the back of the book, how would you find that number?
You can figure out your z-score and take your z-score and convert it back into.
The table in the back of the book is going to have a standard normal distribution, which is z-scores. So you look up and see, well, what's the 85th percentile for standard normal? Then you take the answer that you get back and you convert it. You back convert out a z-score into regular height, and you'd get that same number. All right? So do that real quick. Do inverse norm 0.85 but 0.1 instead of 70 and 3. You got it?
1.036.
1.036. Okay. Now, how did you back that out to get to 73.1? Okay. So z is defined as x minus mu over sigma. So solve for x. Right? So we have a z. We have a mu, we have a sigma. You're just going to algebraically solve for x. So you're going to multiply 1.036 by 3, and then you're going to add 70. I'm just multiplying through by sigma and then adding mu to both sides to solve for x, and you get that. Okay? Now this will probably, it won't be 73.1 exactly. There's some round off error there, but it should be close. Okay, let's talk about the t distribution. Now if you had me for MA346, then you got the story about the student's t distribution. Anybody remember why it's called student's t? Yeah, that's right. Guinness, this guy named William Gossett that worked for the Guinness Brewing Company. What an ideal job for a statistician. And this was way back, it's like 1908, but William Gossett worked for Guinness Brewing Company, and he derived this distribution, which he named the t distribution, because he realized, and I'll get to this in a minute, but he realized that the normal distribution wasn't working very well for his small samples. They were doing field trials with hops and barley and that kind of stuff, and they had small samples. And the normal distribution wasn't giving them very good approximations. So he derived what was the correct distribution, and he called it the t distribution, but the Guinness Brewing Company wouldn't let him publish. That's intellectual property, right? So he published under the pseudonym Student, because he was a student of R.A. Fisher, who's like the father of modern statistics, like the god of statistics, right? And he knew that everybody who was anybody in statistics would know, oh, that must be Gossett, Fisher's most famous student. And And it worked. They did know. But to this day, it's not called Gossett's T. It's called Student's T. So he kind of got lost to history that way. But so Student's T distribution is very similar to the standard normal distribution. So if you have standard normal, this is normal 0, 1, then a T distribution incorporates extra variability. Right? So it means it has to be a little heavier in the tails. It has to be a little wider. Right? So let me see if I've got a different color marker. We'll make this multimedia presentation. A T distribution will have a little more area out in the tails and then a little less area underneath. Now I'm making this way more extreme than it really is. But the smaller the sample size, the further away from the blue curve the T distribution will be. It depends on sample size. And it depends on sample size through its degrees of freedom. So this is a T with n minus 1 degrees of freedom. So for a normal distribution, we say the parameters are the mean and the standard deviation. For a T distribution, the only parameter is its sample size. And it's n minus 1. Right? And as n gets bigger and bigger, what happens to the T distribution? It gets closer and closer to the blue. The red comes up and it converges to the really almost superimposed, and you can't tell the difference. Right? So this is T with large n. This is T with small n. Okay? And that the derivation of the T distribution, this is something that we learn in MA344. But when you make a hypothesis test, you compute what's called a test statistic. Remember that? Remember hypothesis testing? Suppose we want to test that the mean is equal to 0. Right? Against detailed alternative, mu is not equal to 0. Right? What's the test statistic? This should be review for everybody, but don't feel bad if you've forgotten it.
The test statistics were actually false.
Okay. What's that?
Does it become a distribution?
Yes, it does. But you know, if I hypothesize that the mean, and to get a mean of 0, maybe this is mean change in something, like mean change in your allergy symptoms after you start a new drug or whatever. Okay, the mean of 0 would mean there was no change, so that would be what we would call our null hypothesis. No difference, no change. The test statistic that we would compute would be the actual observed mean in our sample minus predicted if what? If the null is true. And so that's 0, right? So minus, in this case it's 0, but in real generic terms we would write that as mu sub 0. The mu from the sub-0 hypothesis. Right? And then it's standardized just like a z-score. And what do you divide by? Okay? I heard several people say sigma. But it's the standard error of x bar, not the standard deviation of x. Right? So what's the standard error of x bar? From the central limit theorem. Man, we're dusting off some cobwebs, huh? Okay, it's sigma over the square root of n. Right? Everybody good on that? So if I divide by sigma over the square root of n, then I have a test statistic that has a probability distribution, what would the distribution of this be if we assume that x is a normally distributed random variable? This would be standard normal, right? X bar is a sum divided by a fixed number, so the sum of normals is still normal. And if the null is true, then this is the mean of all the possible x bars, and you're dividing by the variability of all the possible x bars. That's a z-score, that's standard normal, right? There's one little problem with that formula in practice. What sigma is a population parameter, it's unobservable. You don't know what sigma is. And that's what Gossett figured out. I don't know what the variability of the whole population is. So what do? As a statistician, if you don't know what something is, you estimate it. Don't say make it up. But yeah, you make it up. Right? But you do it in an educated way. But you estimate it. So what's your best estimate of sigma? The sample standard deviation, which we denote as S. And I'll put S sub x just to say it's of the x, right? That's when it becomes no longer standard normal, but T. When you substitute in for sigma a sample statistic, you've introduced a whole new random variable to that formula. So you had, when that was a population parameter, that's not a random variable. It's a fixed number. The only thing that's random, that has variability, is x bar. The standard normal covers that. But as soon as you throw another random variable into the mix, you've increased the variability. This quantity is now more variable than it was before. If you underestimate sigma a little bit, what happens? That makes this whole thing bigger, because you made the bottom of a fraction smaller, right? If you overestimate sigma, then you've made this thing smaller. So this thing has a pretty big impact on the size of this whole fraction through its random error. So then Gossett figured out that, if you use the t distribution, then it incorporates that extra variability, and it's a wider, it has more probability out in the tails. So critical values, like for 95% confidence interval, for a standard normal, you would use 1.96. I go 1.96 standard errors, and I get 95% in the middle. For t, would you go further out or not as far out? You go further out. You got to go further to get 95% because it's not as tall. There's not as much area under here. So you got to go further out to fill in. So critical values from a t distribution are bigger, which makes the interval wider. Less certainty. Right? I'm not as certain about this because I had a really small sample. I had to estimate my standard deviation. So I have a wider interval. Now I'm still 95% confident. So that's the t distribution. Okay? So if you take a normal random variable and you divide it by a standard deviation, you get a t distribution. If you take a standard normal random variable and you square it, what do you get? You remember? You're taking p here soon, right? You better darn well know that. What do you get? Chi-square. It's a chi-square random variable. So this thing is chi-square with one freedom. Then you sum a couple of chi-squares together. You get chi-square with the sum of the degrees of freedom. So if I take z1 squared plus z2 squared, I get chi-square 2. And if I sum up n of them, I get chi-square n degrees of freedom, right? Wait a minute. I said that the other day, didn't I? Sums of squares. Sums of squares of normals are chi-square. So when you have a formula like that's sums of squares of normals. If x is normally distributed, then x bar is normally distributed, and so xi minus x bar is normally distributed. You got a square of a normal, right? And the degrees of freedom on that chi-square is how many things you summed up, right? Now, what if you take a chi-square with a degrees of freedom over a chi-square with, say, b degrees of freedom? What do you get? What kind of distribution do you get when you divide two independent chi-squares? They have to be independent. Oh, God. Nope, it's not chi-square. Come on, Kevin. It's a ratio of chi-squares, but it has a name. The distribution has a name. And it's a letter. F. Yeah, that's an F distribution. And the F distribution has two parameters. Its numerator degrees of freedom and its denominator degrees of freedom. So that's where the normal theory trickles all the way through all of these different kinds of statistical analyses. Right? So you may or may not have encountered analysis of variance. Well, actually, if you had 343, you would have seen a little bit of it, not a whole lot. But that's what it's doing. It's taking sums of squares. So you take each group mean minus the overall mean for the sums of squares due to the model. Then you have each value away from the overall mean for error. So sum of squares due to the model divided by sum of squares due to error. You got chi-square over chi-square. You get an F test. Right? So you get an F test for the significance of that grouping variable. In regression, we're going to do exactly the same thing. We'll have an F test for the overall fit of the model. Okay, so confidence intervals. Let's talk just a little bit about confidence intervals. If this is my test statistic, call it T. In grad school, in statistics, you do things that you learn how to say things like you can always take a test statistic and invert it to get a confidence interval. Right? So I can invert this test statistic. If I use T as a placeholder for a critical value and I multiply through by the bottom, right? And then I subtract x bar from both sides, I get negative mu. Solving for mu, I can end up with mu as x bar minus T times Sx over square root of n. And this is now T critical value. And if I make it plus and minus, I have what's called a confidence interval. Okay, confidence interval. What the heck is a confidence interval? How would you explain it to your mother? My mother can handle this.
It's the interval of values where we know that the mean exists in.
Okay, it's an interval of values that we know the mean, say it again, the mean exists?
Yeah, the value of the mean is in that.
It is in there. And we know that for sure?
Yeah, it depends.
So we're 100% confident?
As in we could say it's 90% confident. Or 90%.
Okay, right. So you need to back off of the we're sure and you become, what were you going to say?
Out of 100 trials, that the true mean would be within this many times. So if you say 90, then 90 out of 100, it will show up to be this.
Right. So we are 90 or 95 or 90 whatever % confident that the true mean mu falls in this interval. Right? So if we use the T inverse function on our calculator, we can come up with these T critical values. Let's say we have a sample of size 10. We'd have 9 degrees of freedom. So this is n minus 1. Do that for me real quick on your calculator. And then we'll talk about why I use 975. But I don't hear any buttons clicking.
I don't have T inverse. I have TDF and TCDF.
Okay, then you got an old TI-84. The newer ones have a T inverse function also.
It's called inverse T.
Yeah, inverse T, that's right. I wrote it wrong. Inverse T.
2.26.
Give me 3.
2.262.
262. Okay? Right, so it's just the inverse of this red curve. The same way as we did the quantiles from the normal distribution, that's a quantile from the T distribution. And it has 97.5% below it. Now, why do I use 97.5% when I want 95% confidence? Because it's two-tailed. I want 2.5% up there, and I want 2.5% down there, so that I get 95% in the middle. But as a percentile, this number is the 97.5th percentile. Not sure how you say that, but because it goes all the way to negative infinity. Right? So that's this T critical value. You get it from a T table, or you get it from an inverse T function, or if you have a calculator like that, you would just do stat, then test, then T interval, and it's going to do it all for you. But take the T critical value, multiply by the standard error, the estimate of the standard error of X bar, and that gives you your margin of error around your sample estimate. So you start with your sample estimate, add and subtract a little bit to get 95% confidence. Okay, so then the book talks a little bit about large sample versus small sample, but anymore with calculators like this and fast computers, we don't have to worry about it. But it used to be that, well, as long as your sample size got big, like 50 or so, then you can just go to the normal Z critical value because it's close enough. Because the tables weren't complete, they didn't have all of those degrees of freedom in it, but your calculator's got any number of degrees of freedom you want built right in it. So there's no reason not to just do a T. So we don't make the distinction between small sample and large sample confidence intervals anymore. So now let's finish out this idea of hypothesis testing. If you have a hypothesis test, you compute the test statistic. You're checking to see how far away is my sample mean from what the null hypothesis said it ought to be. And if it is a long ways away, then you'd say, well, I'm going to reject the null. But how do we make that decision? How do you define a long ways away? Okay, you can do it two ways, one of two ways. You use this critical value, and if this t-test statistic is outside, in either direction, outside of 2.262 units away from 0, then you're going to reject the null. But we don't usually do it that way. What do we do instead? A p-value. We compute a p-value. Right? So what is a p-value?
That far or further away.
Yeah. Yep. It's the probability that the observed sample mean is as far or even further from the hypothesized value just by random chance. Right? Even if the null is true, it's possible you could get an X bar that's way the heck out there in the tail. It's possible. It's just not very likely. So that's called our p-value. How likely is it? When that p-value gets small, then we reject the null. So how small is small enough? Usually we use 0.05. So p-value is the probability of x bar being as far or further from mu sub 0 as observed, as was observed. Given the null is true. So it's a conditional probability. Given that the null is true. Well, what it gives you to assume the null is true is what the population mean is. So then you can come to your normal distribution and say, well, if it has mean 0, then the probability of being way out here or further is really small. Then we get a small p-value. So we reject null if p-value is less than alpha, which is usually 0.05. And alpha is called what? It's got a name. Significance level. That's the significance level of the test. Right? Basically, it's the level that you say, oh, now it's significant. Right? So the significance level. So when we say something is statistically significant, we mean that we've ruled out just chance occurrence. There really is something going on. Right? So if I gave my new drug and the mean change was 35, turns out that's a long ways away from 0, so I get a really small p-value. P-value is a way of quantifying how far out it is. Right? So a really small p-value means it's way out in the tail. We're going to reject the null hypothesis. Okay? What if the null is not true, but you still reject it? That is a type 1 error. Type 1 error. So alpha is also sometimes called the type 1 error rate. Right? Type 1 error rate. I was just working on a clinical study report for a clinical trial that I was involved in, and we had a lot of discussion with the FDA about the control of the type 1 error rate, because we had multiple endpoints that we were analyzing, so you don't get to use all of them at alpha. You have to kind of divide that alpha up across these things, and we had a little argument about how that should be done. So the control of the type 1 error rate, that's the same thing as alpha. What's a type 2 error?
When you reject the null when you shouldn't have. Or, no, you fail to reject the null when you should have.
You fail to reject the null when the null is actually false. Right? Now, she didn't have me for MA346. These guys did, so they were like real careful. Fail to reject. You never say accept the null. And why not? Why can you not accept the null as being true? It has to do with confidence intervals.
Because of the estimation.
That's a 100%. When you say accept, that's 100%.
Yeah, you're saying I'm sure it's that, right? But if let's say I do a confidence interval and I get, for this hypothesis, I get negative 1.1 to 20.3. Right? That's my 95% confidence interval. Do I reject the null or not? I would fail to reject the null because the null hypothesis of 0 is contained in that interval. It's plausible. 0 is a plausible value. Along with every other number that's in that interval, it's plausible. But it does not say the null is true. It doesn't say, ooh, it's 0. It says, it's somewhere between negative 1.1 and 20.3. So 0 is plausible, but so is 1. So is 10. Right? I can't say accept the null as being true based on my hypothesis test. And there is a one-to-one correspondence between the results of a confidence interval and the results of a hypothesis test and p-value. Yeah?
So I think I walked myself in circles on my paper a little bit. Type 1 error is when you reject null when you shouldn't.
Right.
And type 2 is you fail to reject null when you shouldn't.
When you should.
You should. Okay.
When the null is false.
Okay.
And the alternative is actually true, but your study doesn't pick it up. Like this one. I purposely picked one where 0 was almost there, but not quite. Well, if I did this study based on a sample of size 5 and I got this confidence interval, I'd say, well, I can't reject the null. But next year I come back and I do it with 50 people instead. Where's the center of this interval?
It's a positive number, which is not 0.
Right, it's around 10, right? What? Right. So let's say that I come back, this one had approximately 10 for a mean, and I come back, I do it with 50, and I get approximately 10 for a mean. Both samples are agreeing with each other, but that interval is going to shrink a lot because of this, right? The standard error is going to be much less for a sample of 50 than it was for a sample of size 5. So my interval is going to shrink, and now around that 10, I might be, 5.1 to 15.1. Now I can reject the null. Right. So absence of evidence is not evidence of absence. What? Say that 3 times. Absence of evidence. If you take a sample size 5, you've got some evidence, but not enough. You failed to reject. You take a sample of 50, you got more evidence. Now you've got evidence that the null is false. So absence of evidence does not mean, what was it? Absence of evidence is not evidence of absence. Evidence of absence means absence of an effect. There was no change. It doesn't mean that we know there was no effect. There's not absence. There's not evidence of absence. Don't write that down. Okay, looks like the only other thing in that section is talking about one-tailed tests instead of two-tailed tests. So if my null hypothesis uses a less than symbol instead of a not equal symbol, what does that change? It makes it so that you're only going to reject if you get down here in the negative tail, but not the upper tail. So it becomes a one-tailed test. What happens to the p-value? How does a one-tailed p-value compare to a two-tailed p-value? It's half of it. It'll be half of it. So the p-value will be half of what it was before.
The t-value?
No, the p-value. The probability. The t might be the same, right? The t might be the same value, but now you're not looking at as far or further from the null in either direction. You're only in one direction. So you're only adding up this tail, not both tails, to get that p-value. All right? Any questions? All right, let's look at SAS a little bit. Now, for Thilo's benefit, I think I will set this thing. Yeah, that makes it tilt down, but oh well, that's as good as I can do. I can't go behind it because then it doesn't get the infrared signal. So it gives up and it just points at the ground.
Can you hang it, and you can't hang it from the handle at the bottom? Too low.
It's too low. Yeah. So
What if you put
good
it?
enough.
I think it's struggling.
Put the camera further up and then attach the screen.
Yeah, I don't have a tripod, but I need to get one. Tilo's sharp, he'll get it. Right, Tilo? Okay, I don't have an updated document, but I've got this document that I wrote on like introduction to SAS. It tells you how to turn it on, how to get some data in, and all that. But I've got to update it because of the new version, and not everything is working like it's supposed to work. So some of what I had planned to do today isn't going to work quite right, but we'll do the best we can, and then we'll talk about Excel a little bit as well. The first step in getting to SAS. Everybody remember this? What do you got to do first? You got to go to remote desktop. So I have an icon for remote desktop. The thing popped up on my little phone and it said, your battery's dying. So I'm just going to shut it off.